I spent a little bit more time on the first lecture, mainly because I knew that the second one can take a little bit less time. But what I'm going to do in this one is talk a bit more about data, but particularly about indices or metrics or measures for looking at extremes. And I'm going to very quickly give you a review of what I talked about in the last lecture. But given I talked about it within the last hour, and the half-life of memory for most students is longer than an hour, but less than a week, I think most of you will remember it now, but not remember it when you look at the slides in more than a week's time. So it's there really for when you come back to look at this in a week's time. What I'm going to do is talk about some of the things we talked about already quite a lot, and that is data quality issues for extremes. And I don't really need to spend much time on that, but what I am going to do is spend a bit more time on some of the commonly used metrics or indices and get you to think about what you think they are and then talk about what they really are. And there are some classic examples of that, including one that I think is fantastic because it's the most misleading graphic, and it's been produced jointly by the Bureau of Meteorology and CSIRO and shown repeatedly in the State of the Climate reports. So some of you will have seen it, and I'm going to talk about that one quite a bit. You know, I already talked about this. I don't need to talk about it again. I've talked about that. What I'm going to do is talk about indices here. And there are multiple different types of indices. I've talked about it in terms of data quality, but in terms of the metrics or indices, there are really 3 or 4 different types. Typically, the indices, and this is, I think, why I had the definition up before, is the definition in there of an extreme event is the occurrence of a weather variable above or below a threshold value near the upper or lower tails in the range of observed values. It's how you define that threshold, which can be really, really important. Remember I talked about 25 Celsius versus 40 Celsius for temperature? Well, whether that 25 Celsius is near the upper tail for a summer temperature or not depends on geographically where you're located. In Northern Europe, it might be in not the really upper tail, but certainly for Iceland it would be. It isn't for Australia or much of the world. So the reason for looking at this again is that if we pick an absolute threshold for this climate, and there's a completely different climate with a much cooler mean or a much hotter mean, then you're going to get a very misleading set of representation of extremes. There's another reason for showing that graph, because that graph has a mean and a standard deviation representing a normal distribution. If we're talking about rainfall or we're talking about temperature, what happens when you consider longer time averages to the standard deviation? If this is the daily rainfall and the daily temperature, what's going to happen if I talk about the monthly rainfall or the monthly temperature? What happens to the standard deviation? Does it increase or reduce? Reduces. So you're going to have something with a much lower variance. And in fact, you'll probably have something which looks more like a normal distribution. From statistics, the more you average, the more the distribution will become Gaussian. So if you have something which has a much smaller standard deviation, what's going to be the impact on the monthly extremes associated with this location shift of 0.5 degree in the temperature? Is it going to affect the extremes more or less? Someone said something quietly. It does. You don't have to think about it, you just have to look at it. Because the change in the extremes, the frequency of occurrence of those extremes, will be associated with the variability, and a 1 degree or 0.5 degree shift has to be measured relative to the standard deviation. We know that the standard deviation will be much smaller for monthly data and much, much smaller for annual mean data. That's at one side. But what about if we then average over a large area? Look at state average temperatures. Again, much smaller variability than a single site. Or Australian average temperatures. We know often in Australia, if it's warmer in the east, it's colder in the west, or vice versa, because the structure of synoptic weather patterns typically has a scale of 1,000 to 2,000 kilometres, smaller than the spatial scale of Australia. And then when you average over the whole country, you're reducing that variability. What that means is that the metrics that you might use depend upon the spatial scale. And extremes for annual or seasonal averages or large area averages are likely to be either much greater or lesser, depending upon how you define your extreme. So I think I talked about most of what's on this slide already. Small changes in the mean can have much larger fractional changes in the extremes and will have much larger impacts for time averages or spatial averages. It's unlikely for spatial averages that you're going to have as much of a data quality issue. But certainly for time averages, you can have data quality issues that will lead to discontinuities. And in fact, most of the techniques that try to detect changes in site location or changes in instrument type use annual means, both for rainfall and for temperature, because they have much smaller variability, and therefore it's much easier to detect small changes. And those shifts might occur for any range of reasons. Station location shifts, instrument type changes, or changes in exposure. Another critical factor, and I talked about this a little bit already, is how well or how poorly will the data set actually represent extremes, in terms of whether it's a single site location or whether the data set's been gridded, which means it represents an area average value, or whether you're using a model or a reanalysis data set. By definition, a station only represents what fell or occurred at that instrument. And you have to think about the spatial length scale, decorrelation length scale. For temperatures, it's quite large. For convective rainfall, the spatial length scale of extremes can be very short. And that will then depend upon the time scale of the extreme that you're looking at. extreme monthly rainfall actually has a large spatial decorrelation length scale, but 1 hour rainfall often has a length scale, particularly if it's convective. Extreme 1 hour rainfall has a spatial length scale typically of 10 kilometres or less, particularly if it's convective. If it's mainly associated with frontal or larger scale weather systems, it could be larger, but often convective extreme rainfall is associated with length scales of 10 kilometres or less. So for extremes, it's really important to think about the time scale, whether you're looking at sub-daily or daily, or whether you're actually talking about extremes on a monthly or seasonal time scale, as well as the spatial scale and the spatial homogeneity. And I talked about some of that last time. Any questions about data quality? The most important thing that you need to consider is whatever data you use won't be good enough, whether it's models or observations. You had a question in the back.
Yeah, I was wondering which data sets or even field data sets are good enough to look at rising simplification that 10% diet. A lot of studies actually use the threshold, removing certain data sets,
So, do you want the simple answer? None of them are good enough. They all come with their own artifacts. So all gridded data sets depend upon the type of gridding that's used, and all model data sets are dependent upon the resolution. And so you've just got to be really careful in understanding what the limitations of any data set are. And that's critically important, whether it's model or observations, is understand the processing of the data, what corrections, what resolution, what metrics are being used. And hopefully, in half an hour, you'll have a better understanding of some of those metrics. Here's my favourite graph from the Bureau of Meteorology CSIRO State of the Climate, and it says the frequency of extreme heat events is increasing. Looks like it. So the numbers are correct in this graph. It's the number of extreme days with high temperatures across Australia. Yep. No, the numbers are correct. It's for a specific metric. Says it's for heat extremes, heat events. Thomas knows there's something odd with this data. Here's another one. The average number of very hot days. Why are they so different? No, they're both of them across the whole of Australia using high quality data. Same number of observations, same period, same data set.
What is the average? The other one? Total and average?
Nope.
Is there a different threshold?
Nope.
How much of difference?
Oh, they are different thresholds, but they've got different definitions of extremes. And they've got different thresholds, but you would have thought, I mean, this is the average number of very hot days, and the other one said it was number of heat events. If I look at that, there's no justification for saying there's a, whatever they said, rapid increase in heat events. So let's go back to the previous one. Based on what I've said to you already, how do you think you could manipulate the data to show that the frequency of extreme heat events is increasing when it isn't?
Winter hot days?
Sorry?
Including winter hot days as opposed to just extreme heat events?
Well, actually, the previous one included... No, it didn't. It didn't. But I can show you another one that does, and it doesn't show much increasing trend. Yep.
Are there missing events in the earlier time series?
Nope.
that you have base climatology for the whole time period and a mean increase, so you have more hot days at the end, right?
Yep.
So your eye automatically catches the top number of extremes.
Yep.
But if you look at the average, it's a lot flatter.
Yeah, I mean, it's pretty flat until 1950. That's actually what average temperature across Australia is as well. Have any of you seen this graph before? You should look at state of the climate reports. They're really interesting. They are supposed to be a publicly accessible state of the climate information. So, it is from reputable organisations. They didn't manipulate the data too much. The frequency of extreme events is increasing. Well, it appears to show it. So, what did I just say about signals and tails and averaging?
Oh, it's average over Australia, the one. And the other is like...
That's the answer. This defines a hot day as the average temperature averaged over the whole of Australia for a single day. And then calculates the number of days above the 99th percentile for the whole period. So it uses a threshold based on the whole period, the 99th percentile of Australian area average temperature. So how many days on average would you expect to exceed the 99th percentile? I would hope it would be 3.65. 5. Because there's about 365, oh, maybe it's a quarter. Maybe it's 3.6525, roughly. So, actually, if you work out what the average is over the whole period, it is that, but actually in this period, actually I might have got that wrong. It might not be the whole period. It might only be 1960 to 1990 that they used as the base period. I think that might have been it. It might have been 1960 to 1990 they used a 30-year period. But what happens at the end, with a small shift in the mean temperature over Australia, you can rapidly get a dramatic increase. And there has been an increase in the mean temperature. This one, very hot days, is at each station calculate the number of hot days. And very hot days are days above 40 Celsius. And it uses the Acorn Sat sites over the whole of Australia. So some sites have, you go to Northern Australia, Alice Springs, Broken Hill, then takes that geographically weighted average and averages across the whole of Australia. It's really important to understand what that, whatever metric you use, what it means. And I'm going to talk about some metrics and then show you how to use them, because you're going to be doing some labs every afternoon. Well, maybe not every afternoon, most of the afternoons, and then giving a report. And you're going to have a whole bunch of data sets with a whole bunch of indices already pre-computed, which you can use to examine some extremes. But you better know what you're looking at. And so I'm going to introduce you to the sorts of extremes indices that you're going to have available. And you can look at them and play with them and try to understand what they mean. I should point out that this one isn't easily available in any of the metrics that you've got. You could easily calculate it from the data that Thomas is going to make available from the labs, but this is one of the ones that's readily available. So the sorts of indices that I'm going to talk about are not some of the indices that exist for specific weather extremes, like the forest fire danger index that I talked about already. I mean, you can calculate it if you want, but it's not going to be one of the things that you could use in the lab easily. There's another one, the extreme heat index, which is one that is in fact available. Isn't that right, Thomas? You've got it? Anyhow, Thomas will tell you which one it is. The ones that I am going to talk to you about are indices of daily temperature and rainfall extremes, which were originally developed by a group called the ETCCDMI, and then it changed its name to the ETCCDI. It's a group established by the World Meteorological Organization Commission for Climatology and the CLIVAR, World Climate Research Program's CLIVAR program, as a joint body. It's called the Expert Team on Climate Change Data and Indices now. It used to be the Expert Team on Climate Change Data Monitoring and Indices. And it developed a set of temperature and rainfall indices that have been commonly used. They're now available either station-based or gridded from observations. So you can get it for individual stations or groups of stations, or gridded from observations. And it's also available from gridded daily data from models and from reanalyses. And that means it's pretty comprehensive. It's important to understand that for some geographical locations, there are limited observational data sets, and so the data is not available for observations. But it is available for Australia, and it's also available for North America and Europe from observations, both gridded and stations. So many of these are based on indices of days above a threshold, and they're either absolute thresholds or percentage thresholds. But it's important to understand some of the limitations. For instance, if you pick an absolute threshold like 40 degrees Celsius or 25 degrees Celsius, the number of days above that threshold is going to be sensitive to, for instance, differences in the mean, shifts in the location, or to climate change, potentially. But it could also be sensitive to the season. You're unlikely to get many days above 40 Celsius anywhere in Australia in winter. So that means instead of thinking about the number of days in the threshold representing the number of days in a year, it's actually typically, for absolute threshold indices, number of days in the summer or the warm season. Or if you're talking about thresholds like frost days, days below 0 Celsius, or days below 2 Celsius, they're much more likely in winter, as we're discovering in Canberra. So it's important to think about, when you're talking about these indices, about whether you're looking at absolute thresholds or percentile thresholds. Because what percentile-based thresholds do is look at typically the exceedances of either some threshold based on a percentile, which might be the 1 and 99th percentile or the 10th and 90th percentile. And those percentiles are often seasonally varying. So that means that if you're looking at counts above the 90th percentile, the best way to think about that is as a percentage. And on average, you would expect 10% of days to be above the 90th percentile. And if that percentile threshold is seasonally varying, as often they are, it then depends upon The number of actual days depends upon what period you're looking at, whether you're considering a whole of a year, in which case it would be the 36.5 days for the 90th percentile exceedance. But if you're only considering a season, which is roughly 92 days, and it's only 10% of that, and it's only 9 days. That's why often the percentile-based thresholds have counts which are percentage exceedances, not numbers of days. In practice, percentile thresholds are effectively self-normalizing. You're counting the exceedances relative to the distribution and the percentiles from whatever data set you're using, which means they're better for comparing across different parts of a country or between models and observations. So if you want to compare extremes between reanalyses and observations or models and observations, percentile-based indices have any potential bias between models and observations removed. That isn't the case with absolute thresholds. For instance, if you've got an absolute threshold and you want to compare it between models and observations, if it's a rainfall threshold, models tend to have lower rainfall extremes because they're representing area average rainfall compared with single stations or even gridded regions. Models tend to have more light rain days and fewer extreme rainfall days. So if you're looking at absolute thresholds, you can end up with very different answers. The same with temperatures. And part of that can be associated with the spatial distribution. The topography is not often represented well. The other type of index which is used is often the extreme hottest or coldest or wettest day in a year or in a month. And all of those are available, all of those types of indices are available in these ETCCDI indices. And so, for absolute thresholds, I've already talked about this summer days threshold, 25 Celsius, or very heavy rain days greater than 10 millimetres or 20 millimetres in a day. Percentile thresholds, the typical temperature percentile thresholds is counting the percentage of days above or below the 10th percentile for both maximum and minimum daily temperature. For rainfall, it's typically a 95th or 99th percentile. I guess they didn't want to talk about number of days or percentage of days exceeding the 1 percentile or the 99th percentile, because it'd be typically fractions around 1%. And the hottest and coldest and wettest day of the year are all available as well. What I'm going to do now is show you some of these from two different data sets. You can use these data sets off the web, but Tamas has combined all the data and more from models and made it available on Rygen, and we'll talk about that at the introduction to the labs this afternoon. But you may want to do something different or process your own values. You can do that separately using the data sets that Thomas has pulled together, but you can also grab stuff from two data sources. This website, Clingedxorg, was set up at the University of New South Wales by Lisa Alexander and Marcus Donar, funded through a ARC linkage grant now 8 years ago. It is still being maintained, and it provides global gridded extremes data sets and station data sets for these ETCCDI extremes indices from a couple of different observational sources. The Bureau of Meteorology also has a data set on weather and climate extremes, and I'm going to show you how to access some of those quickly through the web, assuming I've still got web access, talking, and I think I will. But this data set has, again, ways of looking at individual sites or area averages over Australia of changes in the ETCCDI extremes and some extra ones that are available just for the Australian data sets from the high quality ACONSAT temperatures and the high quality rainfall data. So this is the Bureau of Meteorology's website, and I'm going to go back to here. This is the information on the extremes stuff. And I'm not sure that you're going to be able to read it all, but this has got information on both the temperature and rainfall extremes. The top set are obviously threshold-based counts for time series. Then there's a bunch of time series which are percentile-based, and then a bunch which are the annual maxima and minima, as well as some other ones like warm spells and cold spells. And then there's a bunch of the rainfall ones. Number of days with rainfall above 1 millimetre, 10 and 30 millimetre, the heaviest one-day rainfall, and some percentile-based threshold indices. I don't have time to go through them all to show you what they look like. You can play with it to your heart's delight. But what I did want to show you was some of the things before. So very hot days is days above 40 Celsius. And we can put a line on there. And based on that, you'd say, well, gee, there's not much increase in hot extremes. We can look at hot days, a bit more indication of an increasing trend. Hot days is above 30 Celsius. What about if we change the approach? I know that warm days is the percentile based. So you've got to remember, and this is the percentile for the number of days above the 90th percentile, where the 90th percentile is defined for the 1960 to 1990 period. So you'd expect the average in there to be about 10%. It's actually 10% for most of this period, and then from about 50 to 60 onwards, it just ramps up. That would suggest, when you're looking at all days across the whole country, this is still just based on observations across the whole country, there's been a clear increase in warm days above the 90th percentile, and therefore likely an increase in, the same thing happens if you look at the 99th percentile as well, an increase in hot events and extremes. But you don't see that with the one that I showed before, which, because of the absolute thresholds at either 35 Celsius or 40 Celsius, ends up being focused on much more on northern Australia and inland Australia. Any questions on that? So this is, yeah, go ahead. Or are you just stretching? Sure. It's the AcornSat. There is an option, I think, where you can pull it out from here. Oh, maybe it isn't. Oh, yes, there you go. Download data. No, it's the data that's shown in the graph. But if you want all the AcornSat data, you can get all the AcornSat data and you can process it and area average it. Yep. Yes, that was in that other page that I showed. So somewhere in here, it has about the climate extremes in micro font, but that's what this page is, about the climate extremes analyses. Is that what you meant, how they've been processed, or about the data set?
Yeah, the steps how each graph is built.
Yeah, basically it's in this page. Yep.
So the approach from the graph you were just showing is to do the extremes over the larger scale. Does anybody does this graph where you calculate for each individual site?
Yes. Yes, and that's the Clingedxorg website. You can get the data for each individual site.
And then do you make a national average out of the...
Or any gridded average that you want.
And how does that look? Sorry.
Did I pay you to ask that question? Any other questions before we go to look at the Clingedx data? Yep.
Why did they choose 1960 to 1990 to average?
Well, so the World Meteorological Organization, of which the Bureau of Meteorology and all other national weather services are part, recommends using a 30-year climatology base period. I might have misspoken incorrectly. It might be 1961 to 1990. It probably says in here what they use. 1961 to 1990 is the base period that they use. And that's because it was a base period before climate started to rapidly change, perhaps. Doesn't really matter. You can adjust it, the thresholds, for any base period. But it's considered to be a period, 30 years was considered to be long enough to remove much of the natural year-to-year variability of climate until climate change started to rapidly affect many parts of the world. But often organisations now choose a base period which is shifted more close to the recent. So the most recent base period that's used in many organisations is 1981 to 2010. And you get the same picture generally. It's just that the 10th percentile would then be the most recent period, and you'd end up with much, much lower values earlier on. I'm going to switch to Clingedx.org. Oh, don't need to do that. I need to do this. So, Clingedx.org, it's hosted at a server at the University of New South Wales. It has both gridded and station-based data sets. So station data set, gridded data set. When you click on view and download data, yes, you can download all the data if you want, but you can also view it. You have to click a box that says you accept a range of constraints. The most important one is that you don't sell the data. It's for research or educational purposes. You're not allowed to download all the data and then make money selling it to some unsuspecting customer. But that's all. And then you get automatic access. So anyone who wants to flog it could say they're not going to sell it and still get it. But I'm not encouraging you to do that. I haven't found anyone who wants to buy it yet. So, I have selected a region. You can pick any region. I've selected a region over Australia. You select a region using a tool which allows you to choose any geographical region. I'm doing this for the gridded data, not the station data. But you can do it for the station data as well. So I've picked Australia because it makes it easier to select the data, to compare it to the Bureau stuff. So we can pick either, do we want to look at summer days? I don't know that there's much point, but we could. I've never looked at it. So this is the, notice that the time series only goes from 1951 to 2018, because that's what, for many other parts of the world, there wasn't good observational data, station data prior to 1951. And I'm selecting time series, not a map or not the raw data. And I click submit. It processed it already. It's not stored, it's processed it. The number of summer days averaged across Australia is, in days, between 230 and 240. That means summer doesn't just happen in Australia based on that metric, it happens for more than half the year. In other words, that metric is hopeless for Australia. There isn't an option in this site to put in your own thresholds, unless you download all the data and calculate the exceedance of the extremes. So I would argue that that one's probably not much use. Well, what about if we go to something more appropriate? So we'll go to warm days. TX90P, you can select a smaller region. You can choose Victoria or Eastern Australia or whatever else. But I'm going to choose warm days. Now remember, this is only for the period from 1950 onwards, the period of increasing trend, and it goes from 9 to about 16. Who remembers what it was from the Bureau? No one. So, in principle, if I've saved that, it goes from about 9 to 15. But actually, if you came right up to the present, it would be up at 16. Gee, it looks like they're using the same region and the same metric for roughly the same data. It isn't the same data. The Clingedxorg uses all sites, not the high-quality sites. That's why it's slightly different. So it's important to understand the Bureau's data is based on the high-quality station data. The Clingedxorg is based on all data that meets certain quality criteria and does some data checking. We better come back to this one.
Is it credit or the duration?
Nope. There aren't many weather stations over the ocean. There are some on islands. Oh, absolutely. In models and in reanalysis data sets, yes, they are calculated in many cases over the oceans. What was I going to do? Oh, I know what I was going to do. We had down, did I lose it? We wanted that one. The next one I'm going to show you is TXX, the hottest day in the year. So the first thing you notice is that you've got, whatever, a 50% increase in TX90P, but for the hottest day of the year, you've got about This is, remember, this is at individual sites averaged across Australia. So it's not the average summer temperature, it's at individual sites. You've got an increase of only about, well, it's from 42.2 to 42.6 and a bit. It's about half a degree. 1950 to 2017, Australian temperatures, particularly Australian maximum temperature, has increased by more than a degree. So actually, in this case, for the hottest day of the year, the increase is not as large as the increase in average maximum temperature, averaged across the whole of Australia. And part of that will be to do with the data sets, and part of it will be for reasons that I don't fully understand. There are lots and lots of other extremes. Who's got a favourite extreme index that they want me to plot? Either from the Bureau or the observational, the Clingedx website. No East Coast lows, bad luck. Sure. We can compare RX 1 day and RX 5 days. Do you want Bureau or Clingedx? Okay. Yep, that's the rainfall from 1 day rainfall amount, the heaviest 1 day rainfall averaged across Australia. It's pretty hard to see a trend. It goes from 60 to 62 millimetres. There is no trend. But let's try. This one. Number of rain days above 20 millimetres. Oh, it's starting to go up from 6 to 8. More heavy rain day events, or that wasn't the one. It must be the 95. They're roughly the same. This one and they are not the same metric. This is the amount of rain in the total rainfall that comes from rain days that have above the 95th percentile. In other words, rain days, the top 5% of daily rain days in a year. How much rain did that contribute to the annual average rainfall, and then average that across the whole of Australia. It looks almost identical to this. This is the number of rain days above 20 millimetres. That's the contribution to the rain. And of course, if you get more rain days above 20 millimetres, not surprisingly, that contributes more to the total rainfall. I've used up all my time. Any questions on any of these? You will learn more than you ever cared to know about these indices when you play with them in the labs. Yes?
I have a question about the data set. So you said about GHCM data set and so daily data archive at NOAA. Are these the same stations that Bureau of Meteorology operates? I mean, GHCM over Australia and Bureau of Meteorology temperature, the same stations?
Yes. but the extremes indices that the Bureau provides are not for all Australian stations, but only for high quality stations over Australia. So the GHC index indices for Australia are calculated for all long-term high quality controlled data sets, whereas the Bureau's ones use only what they consider their quality controlled ones, high quality ones. So it's a different quality process and they're different stations. Does that make sense?
Yes, but the overall stations are the same. So
The starting basis for the stations is the same, but the not the same stations get used in the end for the indices. Yep. Any other questions? Yep.
I just wonder if you could explain the difference between those Zyro plots you showed at the start. I couldn't quite follow the difference between them.
The one that showed the massive increase and the one that was relatively flat. Okay, so the one that showed the massive increase, you take the area average temperature across Australia, and because it's aerially averaged, it has much, much smaller variability than the temperature at each site, at any individual site. So for the area average temperature, you then calculate the number of days for the area average Australian temperature being above the 99th percentile. On average, that would be 3.65 days per year. And what we see, because of a warming trend, is that has shifted the distribution quite a long way. A warming trend of 1 degree, turns out that the variance of Australian area average temperature is only about 3 or 4 degrees. Daily temperature, because it goes up in summer and comes down in winter, but the summer temperatures, the variability day to day is quite small, only a couple of degrees. That means that if you warm it by a degree, you get a big shift in the number of days above the 99th percentile. Now, at an individual site, if you're looking at days above 40 Celsius, or you look at days above the 90th percentile, at each location, a shift of 1 degree is small relative to the summer variability in temperatures. I mean, you think about Melbourne. The variability of summer temperature in Melbourne has a standard deviation of more than 10 Celsius. You can get a range from 20 degrees up to 45 degrees. In fact, actually you get a range from 15 to 45 in Melbourne. In many places. In Canberra in summer, you also get a range in summer between about 20 and 45. So the difference is how big does that shift have in either number of days above 40 or in the number of days above the 90th percentile. And the difference is that as you area average, you've rapidly reduced the standard deviation. Does that make sense? Yeah. Okay. Time for coffee, please.